So it's my pleasure to introduce today's speaker, Karl Berggren from MIT. Our second MIT, we've been 100% MIT speakers this year. Karl is a professor of electrical engineering at MIT and won all sorts of awards and fellow his work is focuses on developing superconducting circuits that can be used to do really interesting things. For example, detect Single-Photon had an enormous impact on the community. So I'm going to cut my introduction short and just let people.
Thank you. Excellent. Thank you so much. So I'm also thinking that I speak more loudly. From just outside of Vancouver. So I had another Vancouver. Okay. So I just let me start by asking a couple questions just so I know who I'm talking to here. So physicists. Okay. The shaking hands, applied physicists. Okay. Electrical engineers. Okay. Mechanical engineers. All right, few. All right, good. I wear a few hats. So one of the hats I wear, I'm actually the head of the faculty in electrical engineering. So Ike Strang was last week is one of the faculty members in my in our department, and we are always looking for new faculty members. So please don't forget, looking for faculty members, send us your resume. That's my shameless plug for applying for jobs. And we don't have an applied physics department in MIT. So electrical engineering is where you want to go if you're interested in applied physics. So was there anyone else programming different? Electrical engineering. All right. So I just we have a group here. There's also a couple of empty slots here. If postdocs are looking, people looking for postdocs, so that's another shameless plug. The folks, I'm going to talk actually about work pretty much, these are the current members of the group. These folks will definitely touch on work that they did, but also, recent former members of the group, and then a bunch of people over the years who've graduated and moved on to bigger and better things. I'm going to start with some very sort of grounded conversation. So first, what is a photon? When we talk about a photon, what do we mean? So a visible photon, you get a sense for it, something like 10 to the minus 19 joules. It's about the amount of energy that you'll get from one pixel of your iPhone coming into one of your eyes in 1 second if you hold the phone a kilometer away from your face. Okay. So it's a long arm, but that gives you how much, and that's a visible photon. An infrared photon is, of course, less energy. The further you go out of the infrared, the less energy it is. It starts to get very, very difficult to detect. A little aside, there's an interesting situation coming on where people can detect microwave photons right now using quantum computers. People can detect infrared photons using our technology and some related technologies. There's a gap in between where people have no way to detect the single photons. So it's kind of an interesting physics problem. And detecting single photons is actually nothing new. So here's a 1936 paper talking about the secondary emission multiplier, which is basically light comes in, it hits a photocathode, and you get electron multiplication. And this was how you did it for many, many years. There's a lot of things that we care about in single photon detection that different applications care more or less. So I'm going to kind of survey them all, introduce the terminology that we're using, and then for your application, you can decide what you care about. Almost everyone cares about efficiency because fundamentally, I'm going to use my mouse actually to point so that people online can see it. So fundamentally, when a photon comes in, that's the orange line here, you want to see a pulse come out. That's a black line. You don't want this to happen where there was a photon absorbed, but there was no pulse. Okay. Reset time is a little more complicated. When a detector fires, typically there's a short period of blocking following that event. some types of detectors, you get a little bit of stacking. You can have a second pulse on top, on the shoulder of the first, but quite commonly, and in the detectors I'm going to talk about, they're fully blocked. So you just don't see a device, a second pulse. If the second photon comes in too short after the first photon. And then jitter, this is another, basically what can happen, there's always going to be a delay between when the photon hits and when the pulse comes. But that delay is not always the same. And so as a result, you get some variance in that delay. And that appears as uncertainty in the time of arrival. Why is that important? Because a huge number of applications actually encode the key information in the time of arrival of the photon. So like LIDAR, for example, an example where you send out a photon pulse and you want to time the photon returning. So that jitter is something we care about very, very much. And then dark count rate, so this is kind of the opposite of efficiency. So this is a situation where you get a voltage pulse, but there was no initial photon. That can happen due to thermal fluctuations or background light. Spectral resolution, this is something that we actually don't have in the detectors that I'm going to tell you about. But in principle, some detectors have the property that when a red photon comes in, it makes a small pulse because it has low energy. But when a green photon comes in or a blue photon, makes a larger pulse because it has more energy. So it has an energy proportionality. That's a very valuable thing to have. The second characteristic that's related is photon number resolution. So a number of detectors can actually tell you how many photons were absorbed. You'll see in our detector, we'll show you an example where we're able to show one photon gives you half the height of 2 photons. So you can count photons with this technology. There's also a tendency for detectors to lose efficiency at long wavelengths. So infrared cutoff wavelength is an important parameter. And then more engineering-oriented things like how big an array can you make? How much does it weigh? Do you need your cryocooler? Can it operate at room temperature? I always tell people that for our detectors, you can still keep the room at room temperature. Okay, so you just have to have a giant refrigerator in it. It's not that big a refrigerator. It's about the size of a photo, maybe something like that. How many of you have an SNSPT in your lab right now? Okay, that is a smaller fraction than I'm used to. I'm used to talking to quantum optics audiences, and the quantum optics audience right now, everyone raises their hands because they're kind of.
I resent that.
Oh, sorry. People raise their hands. Sorry. I don't have a dilution refrigerator in my lab, so okay, I'm not.
You're good.
It's not. If we can share.
We're not friends anymore.
All right, so try to regain our friendship.
Our students are $1 million a year, so that's why.
That was a joke, by the way. What organization do that? All right. The band picture in the same valley is very different from that's why we lose grad students here all the time. Finally, I understand.
They don't get $1 million.
Okay, so what's going on inside the physics of this device? You know, a superconductor famously works by carrying a Cooper pair. So these are bonded electrons that move together through the superconductor, and as a result, don't scatter. There is actually between the state of a paired electron and like an electron in a hole, there's actually an energy cost associated with that. That's why at low temperature it condenses into the superconducting state. And that energy cost is very small. It's only a few millivolts typically. That's why they only superconduct at low temperatures. And as a result, you can come in with a relatively low energy photon, and you excite. I don't want to mislead you here. We're not actually breaking Cooper pairs. It sort of suggests that, but that's not what's happening. What's happening is we actually go into the Fermi state and we pop an electron that's in the Fermi state up into the excited state with our 1 volt photon state. And now we have an electron hole pair. It's technically a quasi-electron, quasi-hole, because at these low temperatures, everything's in rest state. And it can start to scatter. It can scatter off of other electrons. It can scatter off the lattice primarily and generate phonons. And these processes cascade down until you sort of find yourself at the band edge. And at that point, you really need to either recombine with a quasi-pole on the other side, or pair up and make a group, right? And so those are some options, and the problem is, for superconductor, this is poison. Having quasi-particles floating around at the band edge is just the way superconductors stop things. Okay? Well, that's a problem maybe if you're building a quantum computer or something like that. For us, it's great because we want to suppress the superconductivity to make a good detector. That's our goal, is to detect this event, okay? So you can imagine if you have a 1-volt process, you end up with hundreds of quasi-particles, and the superconductivity is quickly suppressed. If you have an infrared photon, you maybe only have 100 millivolt excitation, and then maybe you only end up with 50 quasi-particles or even fewer, depending on how much energy goes into the photon pathway, into the quasi-particle pathway. So then they might not be dense enough to actually make the device switch, and that's the problem for us. All right, so we want to make this easier for ourselves, and so one of the things we do is we pass a bias current through the device. So the bias current effectively puts this system into a non-equilibrium state. It suppresses the gap, makes the situation a little bit easier for us. It also gives us a signal that we can read out, and I'll explain how that works in a minute. There's a very interesting aspect of inductance that is not. Now, when I talk to people about inductance, kinetic inductance, people actually believe me that it's a real thing. 20 years ago, I literally would have to have arguments with like really well-educated people that kinetic inductance is real. But now I think it's kind of in the cycle. How many of you have heard of kinetic inductance? Yeah, okay. This is not true. This would blow people's minds 20 years ago. Go to like YouTube and look up kinetic inductance. And I have the only video explaining it. It was like 2010. Look, we gotta explain to people. Here's what it is. Don't feel bad if you haven't heard of kinetic inductance, okay? Kinetic inductance is just basically the stored energy associated with charge carriers in a conductor. It happens in normal metals, it happens in superconductors. Anytime electrons move, they have kinetic inductance. The difference is in a superconductor, because you can't slow the carriers down, that it doesn't relax, it remains in the device, right? There's no lattice scattering to dissipate the stored energy. If you want to stop these carriers, you have to actually do work to reverse their path. And the crazy thing is, unlike a semiconductor, where you have a high carrier density, so this n is a big number, it means that to carry a microwave in a semiconductor, they can go at like 1 centimeter per second is the typical velocity of a carrier in a semiconductor, because there's so many carriers. Cooper prior density is much lower, factor of 100 or 1,000 lower. And so these carriers are traveling at 100 meters per second. And when you square them, you get a huge amount of energy stored in the 1/2 mv squared velocity, right? So this kinetic inductivity becomes like from a little nanowire that might have 10 picohenries of inductance in a normal system has 1,000 times that, maybe 10 nanohenries, right? So this is something that's unique to superconductivity. It's really cool, and you can tell I'm really proud of it. All right. So what is?
I'm not lying. I checked. It's the first thing that comes up.
Okay. It has like dozens of views.
Dozens of views.
All right.
And some really hostile comments too.
Oh, really?
That's super deep.
Right. So, all right. So what is our detector? We kind of teasing about it. Typically less than 10 nanometers thick, so very thin strip. Okay, maybe between 50 nanometers and a few microns wide. Okay, operating typically we use iodine nitride very commonly, so operating typically at a few Kelvin, less than 10 Kelvin, and producing pulses when a photon is absorbed of a few nanoseconds. Okay, so that's the common thing. This is an early one dating back to the early 2000s, but it's just a nice SEM of it. And these are photoresist on top of the superconducting thin film, typically 90 nanometers wide. You can see there's actually some very cool nano optics in this. Over the years, kind of now that's turned into much more of an engineering problem and less of a physics problem. But you know, when the light comes in here, of course, a lot of the light is going to miss the device, right? So you have to think about how you impedance match to this type of structure to get good absorption. But people are getting system detection efficiencies, as I'll show you, of like near 100% in these things. So why do people care? Well, there's a bunch of things we like about it. So first of all, the infrared efficiency. So I believe this number is about 2 years old, and I think they've done better now. So you know, JPL is leading the way here in this, and getting infrared photons at 80 microns, single photons detected at 30 microns. So for things like infrared spectroscopy, especially looking up into space, you know, this is important also for searches for extrasolar planets. These are key devices that they're looking at. Jitter, so this is work we did with NIST and JPL a few years back. The jitter is less than 3 picoseconds, so I forget exactly, that's about 100 microns of travel that you can sort of tell. So less than a millimeter. A state-of-the-art superconducting detector transition edge sensors sort of held the record here for like 99% efficiency. So now there's 98%, there's actually a few demos where people show 98% system efficiency, means if you have a photon in a fiber, do you get a click? And 98% of the time, if the photon is in the fiber, you'll get a click for this particular device. Count rates, actually, this is a slightly dated slide. I don't know, got the wrong version in here, but now they're up at around 1.5 gigacounts per second. Dark count rate, this is a result we did a few years ago in our dark matter search, which I'll talk about later, about 1 count per day, and operating up to 20 Kelvin. Oak Ridge showed this 7 Tesla fields, and I should mention, by the way, well, let me get to that in a second. Another important thing is they're fairly easy to fabricate. It's a single metal layer, single step of lithography, and a single etch step. Okay. It doesn't require magnetic shielding, which is a key advantage. And you can use a room temperature amplifier, you don't need a squid amplifier or anything like that. So these are all advantages. One thing I should admit, though, is that these are sort of hero experiments, right? These are like each of these is like a PhD thesis for someone, right? This isn't something that you can just dial in a detector that can do all of these, right? So don't get too excited. All right. So some of the applications, I think, obviously, people here are probably more interested in the quantum applications. So I'll touch on those briefly, but you know, this field started out, at least in the US, very much motivated by deep space communication, right? We spend billions of dollars to send spacecraft to outer space. We equip them with spectrometers, seismometers, you know, microscopes, etc. We generate data in these spacecraft. They're basically floating labs, right? And we generate data at incredible rates, gigabits per second. Data comes back to Earth at the speed of like a 1980s modem, right? So you're waiting days before you get your first like color photo. It's like a week to download like a nice video, right? So, you know, these types of situations are really, really constrained by the data rate, right? And these detectors enable much, much higher data rates for that deep space communication, basically by encoding the data in the time of arrival of the photon. So it's like you walk up, you know, it's like an old spy novel, right? You walk through a lobby and somebody hands you a piece of paper with something on it. But the code is not what they wrote on it, it's the time that they handed you a piece of paper, and that's like the key thing. So that's what you do with these detectors. You have them 2 synchronized clocks, one on orbiting Mars, that's not been demonstrated yet, it was done orbiting the moon. But you know, they have 2 synchronized clocks, and they use, based on the time of arrival of the photons, they can encode up to 10 bits of data per photon received with this method. So it's a very time efficient, very power efficient communication scheme. And there's this beautiful demo, Emma Wollman at JPL, who's the lead engineer on this. You know, they have, I think it's 140 million miles away, this asteroid mission. They downloaded this video of somebody's cat chasing a laser pointer from the Psyche mission. So
I thought you were going to say they aimed the laser pointer.
no, very careful. No,
That's a big aperture.
Interestingly, cats have incredibly good eye sensitivity for light, but they don't detect single photons with their retina. They actually have a threshold set at about 10 photons, and the hypothesis is to avoid shot noise when they're hunting at night, so that they can, you don't get flicker. So anyway, I'm not a biologist, wildlife biologist. I don't know if that's true. Yeah. All right. So there's a fair amount of heckling in this audience, I've noticed. Not great. Thanks. All right. All right, so let's move on. Another very cool application of these things in transistors. So when a transistor switches, you have a 1-volt photon that then decelerates to the ground across the channel, and that's just a few nanometers, right? And there's actually a fair amount of well, when you decelerate an electron, you emit Grimshaw radiation, right? And so actually, this comes out as infrared radiation from these devices, or these detectors have been used to image the operation of an integrated circuit in real time from this very, very faint level of this Grimshaw radiation. And it's work project we did with IBM and another company that to try to use this to actually look for, to verify that the circuits are what you think they are in that integrated circuit. And finally, well, not finally, but LIDAR, another big application area. I mentioned it already, so I'll skip through it relatively quickly, but we just got a result showing sort of millimeter level resolution, working with Robert Hatfield's group at the University of Glasgow and JPL on this, and we made the device that they used for this demo. The Chinese groups are now doing maritime fog detection, which is quite interesting. It's hard to see fog from above because it's quite thin when you do it from above, but when you look in plane, you can see it. So this is, I think, at Tianjin University in China, and they've used this. And you can see here this tiny amount of reflection of photons from this bank of fog that existed between these two islands in the bay there. So for maritime safety, this is important to try to see where is the fog, because that's a hard question to answer. And then also from China, an interesting experiment recently where they looked up and they reflected the light off of a satellite that's going by, and then used the time delay from that reflection to tell the exact altitude. It's actually a hard number to get at. And they could then tell the altitude to within 8 millimeters over a distance of 3,000 kilometers using this method, right? So this is important because if you wait too long to correct an attitude, a satellite's orbit, it takes a lot more energy to get back into the correct orbit. So the faster you can do that, the better. There's a number of companies that are making these detectors now around the world. Photon Spot is one that's spun out of our lab a long time ago. Quantum Opus came out of NIST. Single-Photon came out of Technical University of Delft. ubiquitously is, I think, collaborating with them. And then Scontel is actually the inventor of these technologies, as Jeremy Goldsman is based in Russia, and then Photech in Shanghai. And I think there might be another company that I'm forgetting. I think there's one in. I think there might be one. I shouldn't speculate, but I think there's one more that I'm forgetting. Okay, some biological applications we've looked at, trying to use these for fluorescence lifetime imaging in systems, looking for basically when you put a certain fluorophore in a certain chemical environment, it often will still fluoresce, but the lifetime will change. And so if you can map that lifetime change locally across the cell, you can kind of tell what parts of the cell are functioning as expected and what parts are malfunctioning. Okay, quantum. So very famously in 2015, a number of groups pursued this goal of trying to demonstrate a loophole-free version of the test of Bell's inequality. So test of Bell's inequality, basically says, if you can choose your basis locally, right here and randomly, right? And you can look at the correlations between them, you can rule out the possibility that there's an underlying variable that was shared at the generation point of the 2 photons. You create 2 photons, from a single source. And if you can, and you can sort of establish their entanglement is non-local through a local measurement here and here that is space-like, meaning they happen at the same moment of time, and they can't exchange information at the speed of light in the time to do the measurement. So that's the core idea of this cell test of quality. And this was done by the NIST group using these single-photon detectors. Because they're so fast, they only have a few meters, maybe this is 200 meters, so that's something like a microsecond that they have, less than probably 100 nanoseconds that they have. So they have to do the measurement, they have to do the random number generation, the choice of the basis, and the detector measurement all within that time frame in order to realize that. Quantum key distribution is another area where certainly in the first sort of 20 years of that field, all of the records were basically held with these detectors, and that fundamentally comes about because one of the key metrics is how far you can transmit a key at a certain rate. The further you go, due to loss, the rate at which you can transmit a key drops steadily. And because these detectors have a very, very low dark count rate, you can do it further with them. So I think 400 kilometers or so was the record, at least as of 2016, 421, 2018. This has also been done in free space over long distances, but all of these approaches take advantage of that high efficiency to dark count ratio associated with these detectors. And now more recently, just in fact, I'm visiting these folks on Friday, there's a company now making these SNSPDs in very high volumes on integrated circuits for interface directly with photonic quantum computing. So this company, Quantum, which has been very successful in raising funds and is pursuing it's a joke. But anyway, they make these detectors now by the thousands in a boundary integrated circuit process. One of the things I find very interesting about the way they're doing this is that a lot of the things that sort of discussed in the field for years and years, but this is one of the most interesting, is that the detector is actually fully enclosed in a little metal box. And that's to prevent scattered light, pump light from around the single photon generation section or other waveguides nearby from getting in there and polluting their detector. So I thought that was pretty interesting. And this actually, Faraz Najafi, who ran that effort for many years there, is actually a former student of mine and has now moved up in the organization. So I'm going to spend a little bit of time talking about this particular application to dark matter search. So dark matter is an interesting property. For those of you who have not been following it, we know it's there for a number of reasons. So first of all, there's this plot, a very famous plot of the velocity of the star versus its galactic distance from the galactic center. And that if dark matter wasn't there, then there wouldn't be enough gravity to explain that plot. We also see gravitational lensing, and the degree of gravitational lensing that we see can only be explained by dark matter. It explains galactic collision dynamics, so we can see images of galaxies hitting each other, and there's not enough mass to explain the dynamics that is seen without dark matter. And also there's an inhomogeneity in the cosmic microwave background that's currently best explained by dark matter. Now, maybe it's not there. There's two kind of nightmare scenarios. First of all, it's not there. Okay, then all of this physics is wrong. We don't understand gravity. We don't understand, people typically don't think that's right, but there's certainly some people who take that seriously. So, and then the other nightmare scenario is that it completely does not interact. It's perfectly dark. Okay, in which case we can look and we'll never see. right? The reason we can't see dark matter is because it won't interact with the electromagnetic. So literally it doesn't interact with light, right? It only interacts with gravity. And we don't have gravitational sensors that are nearly sensitive to detect that. Okay, even LIGO doesn't even, right? So, the question is, does it interact electromagnetically at all? And if so, how much and what wavelength ranges? You know, what energy ranges? And we got interested in this theory paper by Masha Baryaktar and colleagues, and in it, they had this idea that even though dark matter shouldn't interact with, or may not interact strongly with like an electromagnetic medium like a dielectric, one of the reasons its interaction is so suppressed is because of energy momentum mismatch. Basically, the momentum of a dark matter particle does not match with the momentum of a photon that would generate the same energy. And if you can't match momenta, you're not going to get a scattering. Okay, so they like to have the dark matter particle come in and generate a photon. They like that scattering to happen. And in principle, it might, but it's not just going to happen in a bulk medium because of the momentum conservation. It could not happen at a medium edge, however, because at an edge you have a discontinuity in the spatial Fourier transform, and therefore you have a lot of momenta present in that edge. And in fact, in a periodic edge, you can really strengthen for it. If you assume you know the dark matter energy, you can really strengthen the exact cross-section for interaction with dark matter. Okay, so that's what they tried to do. That's what their design was. They had a bunch of ideas about putting a gas in there that were, you know, maybe a little optimistic about what experimentals could actually do. But so what we built instead, working with trials like this and my postdoc Ilya Taraya, they actually just did two different dielectrics. Okay, made a multi-layer stack of two different dielectrics. It turns out in this layer that increases your cross-section for interaction by n squared, where n is the number of layers that you have. So as you add layers, you win and win and win. And this is the target. This is where the dark matter is supposed to come in and generate a photon in this bulb. And then we just put a lens on top of it, and it focuses down on the boost one of these. And why is an SNSPD important for this? It's because of the dark counts. Fundamentally, the SNSPD, any detector that has dark counts here, you can't distinguish between a dark count and a dark count. Right? And so you're gonna so you really need a detector that has essentially no dark counts for this experiment to work. So we built the thing, packaged it. You know, it's just a bunch of Thorlabs components. Basically, the trick is all in the device here. And then some care in terms of doing the thermal engineering right so that things stay aligned when you cool them. Obviously, we had a control chip right next to it that's not at the focus. So one of the chips is at the focus, one is not at the focus. And so if you see the same click rate for the two devices, it means you have no evidence for dark matter. Okay, and it's really important that, because if you have evidence for dark matter, your life is going to become very complicated very fast, right? So you want to make sure you do your controls correctly, right? So, so this is the box. It sits through Calvin, it gets wrapped, and then it gets wrapped again, and then it all gets put into a 300 millikelvin cryostat and cooled down, and you wait. Right, so this is the normalized counts versus the bias current, okay? And you see for this device at two different wavelengths that it has a nice wide region here where the device is insensitive to small variations in the bias conditions. So that's where we want to operate. But if we operate too high up here, we start to get darkness. Okay, so we back off as far as we can. We operate at a point where we have efficiency but no darkness. Okay. And by the way, this is the dark count rate with fiber attached. This is the dark count rate without fiber attached. So obviously the fiber guides into the background. So we have to do the experiment with fiber. So we calibrate the detectors first and then no fiber. And then you sit there and you see 5 or 6 counts over the course of a week. but your control chip also gives you weak. So sorry, I guess you probably could have guessed how this story ends. We did not see dark matter. But if you're in the game of searching for dark matter, basically the trick is you look at the coefficient in your Hamiltonian that gives you the strength of this interaction term, and your goal is to push the upper limit of this value down as low as you can until people start to reach theoretical limits here that tell them that that are inconsistent with their expectations from various models. So so then you're basically trying to sweep the possibility of dark matter out of this parameter space. And this is what we did. This was the limit before, and we pushed this little bit.
But it's a log scale.
It's a log scale. That's the problem too, though, because it turns out on the x-axis here, we're showing you 1 order of magnitude. There's 90 orders of magnitudes where it might be. You could at 1 million for grad student, it adds up to. So obviously we can do better, okay? And with small improvements in experiment, and also it's a fairly inexpensive experiment in the scale. We have another idea. If you're interested, go to the archive, look up this paper in the archive. It's in review right now. Basically, instead of using a multi-layer stack, the idea is we just use a dielectric powder. It's all surface area. All that surface area gives you momentum matching, right, between the dark matter and the photons. And so you can get a much more massive volume. Okay. It also traps photons. If you have a photon that is, let's say a dark matter particle comes on and generates a photon in here, that photon actually will go in, diffuse, come out, diffuse, come out, diffuse again. Okay. These dielectric powders are very, very low absorbing. And so we actually think this is kind of a cool combination of like a good dark matter target and also a good collector of photons and putting it into our detector. I mean, this is theory, so remains to be seen whether it can be built. And fascinated to see what the reviews say. But yeah, at least we've survived the going on the archive, which is not always easy. All right, so I want to get back now to a broader discussion than just the superconducting nanowire single photon detectors, because the device is fundamentally kind of a digital device. It basically tells you about the existence or lack of existence of this photon, right? So it's kind of taking in the physical world and generating information, right? And so for a long time, we kind of thought, well, geez, it must be possible to do something more than just sense with this wire. Maybe you could do some actual information processing with this wire. So to explain how that would work, I got to explain how the IV curve. So because I'm electrical engineer, current always goes on the y-axis, voltage is always on the x-axis. Everyone else is doing it wrong. And the superconducting branch is therefore on the y-axis, where you have 0 voltage generated. And we bias the device to just below that bias. And so what will happen is if anything sort of hits the wire, the critical current is suppressed. So this is the critical current, the maximum current the superconductor can carry. And now this is no longer a valid state of the system. The system has to switch over into a resistive state. So that's the way you think of it as an electrical engineer. As a physicist, you think about it more in terms of the microscopic physics of what's going on. You have a biased wire here. This might be the circuit. Remember the kinetic inductance. Okay, so we model the device as an inductor first and foremost. And then this load. What is this load? It's your amplifier. It's the thing that's going to sense the voltage. Okay, so we call it a load. And we just put a bias current, of course, because this path is resistive. All the bias current goes through the middle. Okay, so that's all of this. And here we are at 0 volts, DC current. Nothing interesting is happening. Photon hits. Momentarily now, you're still having a supercurrent coming by, but you've got a hot region here, which has kind of distressed the superconductor and pushed its critical current down a little bit. And so we're at the moment of finally seeing a voltage. We still don't see a voltage. Okay, we maybe see some slight inductive voltage. It's too small for us to sense. But because we've exceeded the critical current, something happens. We can go into that. That's like a whole 20 years of research. People are thinking about what happens. Vortices are generated. Answer, but and you get a resistive region appearing across the wire. And as a consequence of that, there's now a little bit of resistance in series with this inductor. And therefore, there's a little bit of current going into your amplifier. So you're starting to see a little bit of voltage appear. And that voltage is going to grow as the current shifts more into the amplifier and away from the device, until finally, this resistance is so big, it's typically a kiloohm compared to a 50 ohm amplifier, all the current's going in. And because there's no current left in the device, there's nothing left to heat the device. And as a result, the heat just dissipates into the substrate and the system is restored into a superconductor. Now you can see that's going to depend a little bit on the load. Okay? If that load was really, really high, that wouldn't happen, you'd latch into a steady state. But in this mode, with a low voltage, low resistance load, it self-resets. And here you are, you have all the current going into the load, you get your maximum voltage, device is superconducting. And now it's just a question to wait for the device to reset, which you can do. So you just wait, 2 nanoseconds, typically somewhere between 1 and 10 nanoseconds, and the device ends up back in its superconducting state. All right. However, there is this kinetic inductance, and this kinetic inductance actually helps us now in a second totally different way. Okay, it actually, unrelated to the reset time, it actually changes the speed at which the electrical signal moves in the superconductor, and that's because we're all used to specific capacitance. It's going to be epsilon r times epsilon naught. That's like the capacitance per meter. But now there's also an inductance per meter, and it's hundreds of times bigger. Just like the mu naught, the magnetic permeability is like 100 times the magnetic permeability of free space, which means that the speed of the signal is a tiny fraction of the speed of light, and the wavelength of the signal is a tiny fraction of its traditional wavelength. So you've got this very, very compressed microwave circuit now, maybe 100 times smaller than you would normally need to make the device work. So for instance, so this is just a plot. Depending on the center conductor width, you get higher impedance or lower impedance, you get faster speed or lower speed. You make a narrow wire, you can get this signal to travel at incredibly low speeds. You can make microwave circuits that are massively reduced. So here's a microwave coupler that we designed and built, and the whole thing fits into, this is all impedance matching, so this doesn't really count. From an integrated circuit point perspective, right, you could just work at the impedance here, but it's down at a 0.5 millimeter squared, versus 5 millimeters squared for a conventional device. So able to screen a much larger device and able to make image resections. So somewhat surprisingly, you can use this very, very slow speed to give a time delay image. The way this works is a photon hits, and then you timestamp at the 2 ends, okay? And basically, if you know when the photon hits at the 2 ends, and you know the speed of light in the system, you can calculate exactly where and when the photon hit, right? So you have a nice setup there. We showed some years ago now. These are just, each one of these dots is a single photon coming in, hitting it, causing these 2 timestamps, and then post facto calculate where it hit, and then we make the video based on that. And obviously, they're MIT students, so they make an MIT logo with that. So we shine light through a mask that had the MIT logo to do that. Recently, NIST has done something based on this related idea, also using this time delay, but then multiplexing in a clever way to make a very large imaging camera, 400,000 pixel camera with this. All right. So I'm gonna skip this. This is the work that I alluded to on photon number resolution, but I'm running a little short on time. So we can come back to that if, actually, this is a quantum audience. I should tell you about photon number resolution. Okay, I'm gonna skip some of the digital electronics, so sorry about that. But the basic idea here is that, let me get back to the circuit. Yeah, maybe this is an interesting story. So when we did that imaging experiment, I remember distinctly we were looking at these traces versus time of these pulses, and they have these sort of shapes, right? Each one of these. We were looking at them one at a time. We said, okay, let's look at them all at once on the computer. We had 50,000 traces. Let's look at them all at once. And this is the plot and map. And what's amazing is of those 50,000 pulses, there were a few that went, like dozens, that went above that were clearly distinct in a qualitatively different way. Classifier would just be like, yeah, I can see that. And then a few more, very few more, that had this shape. And our conclusion at the time, and it's borne out, is that these are two photons. What is happening here is two photons have been hit on this transmission line, and instead of getting this nice clean propagation of the signal, you get some propagation out, then you also get hit a hotspot of the other wire and get some reflections. So it just gives you a little bit of a different kind of overall view of it for these rare events. And we found a way to take advantage of that. Basically, if you have two photons that hit at once now in a compressed wire, not a transmission line at all, just a compressed wire, you actually get twice the voltage locally. There's two resistors now that are in series with bias. And so in principle, you should see some events that are at a certain amplitude, and then you should see some events that are twice that amplitude. Unfortunately, the whole system is kind of shorted out by your amplifier mode. And so you don't see that full doubling of the voltage, but you do see a significant increase in the voltage, okay? And enough so that you can clearly distinguish single photon events from two photon events, and maybe from three photon events, depending on how. So it is possible to do photon number resolution with this. All right. So I'm gonna just take maybe a couple minutes more to tell you about another direction that this has taken us. Referring to my comments about information earlier. And that is to try to do computing. So in superconductors, typically people use Josephson junctions to do computing. All right, so if you're familiar with them, you'll know what I'm talking about. If not, this is probably not enough to explain it, so I'll just skip it. But they're great devices. They're very, very fast. They are.
That was a pretty thorough.
There you go. Yeah. 30 seconds. That's all just the junction really needs. It's a tough problem. Their physics is very interesting. And they've been used to develop really impressive digital electronics at this point. The problem with them is the physics is kind of distracting in a way. I mean, it's too interesting. You spend time thinking about the physics instead of just making circuits, I think. And there's a lot of problems associated with them being small, they're easily affected by magnetic field, they're being relatively hard to fabricate, and nobody can make high temperature versions that work in these high temperature superconductors. They can make them, but not in large streams, okay? So there's very interesting, before the Josephson junction came around in '62, before there was this guy, Karl, he did a lot of interesting things, but one of them was invent this device. It's a superconducting wire with a loop solenoid. And you run current in the solenoid to apply a magnetic field and thus suppress superconductivity. It's called a Cryotron. And until the 1970s, it was very actively pursued, especially by the intelligence agencies, trying to make really, really fast computers to do things like code breaking, stuff like that. It was viewed as a really exciting approach. So one of the things that's interesting about these nanowires is that they actually can be used to do computing in a way that's very similar to these cryotrons. Instead of using magnetic field, we just use heat to turn the cryotrons on and off. Basically, we bias them just like we bias the superconductor. And then depending on the load that the device sees, it switches into one of two states. One can be called the 0, the other can be called the 1, and you can do computing that way. I think, I'll just give you a sense of some of the circuits that we've made using these devices over the years. So, for instance, this is a neuromorphic computer. It's designed to work. It's given a neuron, basically a model of a neuron. Instead of pumping, sodium into the cell and potassium out of the cell, it pumps magnetic flux lines into a loop and out of the loop. And whenever the current builds up too high in this loop, it has a threshold that it shoots out some flux, and we can show a bunch of behaviors of this simple circuit that mirror the what's called the Hodgkin-Huxley model of neuronal physics. And SNSPD is not that different from this device. It's just, this is a device that is still it's fired by going over the threshold, not by receiving a photon. So it spikes, You can do the same thing with heat. So you can apply a heater to the device that makes it fire. So instead of the photon hitting it, you just add heat. This is what it looks like. It just has a gate here and a channel. And we've made now a 4x4 memory with this. So this is a bunch of read lines and write lines here. So the data comes in along these blue lines. These are the superconducting lines. And then if you want to write the data into the loops, you put a voltage along these lines. Exactly how this little cell works is a little complex, but we were able to show that it works, and this is now on the archive and being reviewed, and this is just the operation of that memory cell. We have a version of this called an Entron, which is a 3-terminal version of it. So basically the way this device works is you pump current into the gate here, and that causes this choke region to switch. That injects quasi-particles into the channel, so then the channel gets its critical current suppressed. Now the channel switch works very much like a transistor, except it's current injection rather than voltage level. And this is a simple inverting amplifier topology. With that, you can actually make SNSPD readout amplifiers, and actually this is a half adder that we built, simple digital circuit with this technology. And now the students are kind of going, really taking this a lot further. So here is a ripple counter, which is basically just a loop that sits here and integrates every time an SNSPD fires. Every time an SNSPD fires, it adds flux to this loop. Once it's fired enough times, that triggers the next input. And then it starts to integrate into this loop, so it can count in phase 2 and phase 3, so forth. And we have something like that working with the shift register now. Basically just you load flux. Where's the best way to put it? Maybe a little bit too hard to sort of explain it given the time we have left, but it's a fully functioning shift register. So for you could imagine a situation where you have an imager where there's a bunch of photons that are absorbed, and now you want to shift that state out to a readout circuit, right? So you could potentially load it into this circuit. Okay, and then finally, very, very recently, we published a paper where we actually made a diode using this with a small magnetic field attached, a few millitesla of magnetic field attached, and this diode can be integrated into 4 of them, and we're able to make a full wave rectifier, which allows you to create a current source on chip. You can AC source in, rectify it, and make a DC current source on chip. So you can imagine for power handling on chip, it would be interesting. So I'm going to wrap up now. I'm running close to the time here. I just had to tell this little story about the Cryotron, which is after working for several years in these wires, we discovered that at MIT they had buried one of these Cryotrons when they built the building 20, which is the building where probably a lot of you know, building 26, where all the AMO work happens in building 26, Ketterly and Pritchard and these people. Anyway, when they built that building, they buried in the basement of it in the foundation, they buried a time capsule with a cryotron. And they said they wanted to do that because it's going to replace the complex tubes and expensive transistors in electronic computers of the future. All right, so cryotrons are the future. And they knew that all the way back in 1957, right? And what's crazy is that when they built our new nano building, it was too close to the foundation of that other building. And go to this link. And you'll hear the story of what happens next. I'll let you take a photo of it because I don't have time to show the video. But it's crazy. They found the things. And you can imagine they kind of freaked out this big glass tube buried unexpectedly. And it said on it, do not open until 2957. And I went to the museum with my grad student, Adam LaPron, who was doing all that work with me. And we found they wouldn't let us open it, but they let us shift it around a little bit. And we found the cryotron. It's here. It's this little wire. It's a wire solar drop. And he says here in Buck's handwriting, which I just got chills when I read it. 0.009 inches of tantalum wire with 0.00025 is an amplifying device based on the magnetic destruction of superconductivity. Operation temperature 4.2 Kelvin. So there's a book about him. If you're interested, he died very young. Speculation was it was the middle of the Cold War and that he was killed by the KGB. That's the speculation. The book makes a case for it, so you can look it up for yourself. So I think I'll wrap up there. And I want to thank, of course, a large number of people that we've collaborated with over the years, as well as financial supporters and all the other people who are in this field. This is a big field. I'm not the only person who has made a contribution. Yeah, very happy to take questions if you have. Okay, thank you.
Yes, I have like a very naive question, but earlier you were kind of talking about like this higher cutoff as like
Yeah.
I guess figure of merit.
Yeah.
And you also had mentioned that kind of like these like work by absorbing a photon and then get a cascade of like,
right.
quasi-particle shenanigans.
Yeah.
Eventually you end up above like this is one gap. Why can't you like do the T and think more like what is the trade-off by like kind of going
into the gap
TC
yeah.
or and kind of bringing that gap like very close to zero?
Yeah.
What you lose.
So this is actually kind of a controversial question. So I think a lot of people would just tell you that there aren't enough quasi-particles generated because the gap can't really be suppressed to zero. And the critical temperature sort of sets the scale. And whatever it is, if you need 1,000 quasi-particles or 100 quasi-particles or 10 quasi-particles, with larger TC, it becomes harder, smaller TC, it becomes smaller. My personal feeling that's kind of directly the question is that the problem is stability with which we can set the bias conditions. So we need to stay far enough away from that edge gap so that current noise, thermal noise, magnetic noise, all of those things don't start to trigger false alarms. Compared to a TES, see, we have two stages of amplification. We have the initial cascade of the photon that generates the quasi-particle. We also have this vortex flow that happens afterwards that creates the hot spot. And so if we get too close, if we bias too close, so that we get a vortex generation just thermally or just from fluctuating magnetic field, that's going to appear as a jump. So I think the short answer to your question is, if we try to do that, we get thermal.
So I'm an SPCM guy. There you run a lot.
Sorry.
They're cheaper, man. Not as good, but they're cheaper. With SPCMs, we worry about like trap charges and stuff and after pulsing. Is that an issue with SNSPD?
It seems to be much less of an issue. It can appear if there's a little bit of latent heat left in it, so you bring the bias curve back up too quickly, can refire, but the time scale is like 10 minutes for that, yes. So as opposed to microseconds.
Yours is, and this is passively quenched. Do you do any active quenching? Or is that-
No, there are people who do actually.
So in your earlier slides, you mentioned one of the application as QKD. I had this question, how does SNSPD help increase the distance QKD can carry securely?
Yeah. So so let's suppose that we start with a fixed, we have a certain amount of light that the fiber can handle, right, before it starts to melt, non-linearities. And then, you're going, you start to attenuate to go further and further. Fiber, and I forget what it is, this is something like 100 kilometers. They need to restore it. Anyway, so 10 dB over 100. 10 dB per 100 kilometers. Okay. So basically the idea is, if you have a detector that has a certain dark count rate, right, that sets a limit to how much light you can feed in at the origin, basically. And so by having a detector with a lower dark, you can now go farther and still have a decent signal to noise. And the trade-off is with the bandwidth, and I don't have it at the top of the head, like what exactly, how the bandwidth figures. But roughly speaking, it's like Shannon's, you get better signal to noise, you get better bandwidth.
What's the prospect for like counting higher numbers of photons? Like, do you think it'll be possible to get up to like 4 or 5 from a single device? Is that like an engineering thing?
Yeah. I mean, you could do it with an array. If you have a big array, you could do it. People are doing like 32. I think I saw a poster last week at a conference where they were doing 32 arrays, and I think they were doing. It was pretty impressive. It was probably 5 photons pretty recently, but it was not a high efficiency array. You need an array with, I know it was pretty good. Maybe it was like 70% or 80% efficiency. But if you want to get above that, you can't have loss in your system because the loss completely masks the photon. So it's going to be a really difficult engineering problem, combining really, really high signal to noise range, really, really high efficiency with a big array. I think the possibility of intrinsic noise resolution, photon number resolution, I don't know what it is fundamentally, but practically it's 2. We can distinguish 1 and 2 very, very confidently. Between 2 and 3, there's a significance.
Yeah, I can ask some questions. So I was just wondering, you have these spiking neurons, and do you see a path to real morphic quantum computing or accelerator for learning?
Yeah, I was really excited about this work for a long time. There's a couple of reasons we haven't pursued it as actively in recent years. One is that Josephson junctions are going gangbusters in this area. There's a bunch of work, very analogous work in Josephson junctions. That was the work that inspired us initially. And that work is lower power, it's higher bandwidth. There's a lot of reasons why it's perfect. So we sort of just didn't see the comparison. The second reason is I learned more about how neuromorphic computing is happening now in semiconductors. And one of the things most people probably know from large language models and machine learning and so forth, is the digital approach has incredible efficiency in being able to prune, reduce resolution, and otherwise like massively simplify the problem and accelerate it. So these analog approaches based on spiking, I think, are interesting from the point of view of like, how do we understand how the brain works? How do we kind of build machines that act like the brain? But it's kind of like making walking robots. Like we're just at the point now where wheeled robots are just much, this isn't a good example. When I was your age, people would make walking robots, and they were bad at doing robots. And instead, you would obviously want to use a car to get around, not a walking robot. Right now, they're good walking robots. It's kind of the same thing. I mean, I think this neuromorphic computing is to see if we can make computers that work like the brain work, not to see if we can make computers that are better than conventional. Not yet.
So one more question. You had that superconducting rectifier. Is that a dissipative device or is
Yes,
it is
100%. All of these devices are actually dissipative because the way this device works is it allows current to pass this way, but when it passes this way, it switches. And that has to do with the way current crowds as it goes around this corner versus the magnetic field. For certain direction, the current adds to the visor current in the magnetic field, and in the other direction, it cancels destructively and reduce the current density of that one.
So does this only work up to at some above some minimum power level? What is that power level? How much do you have to dissipate to get the
Yeah, I think each of these switching events is about an attojoule, so it'd be about the frequency times maybe 10 attojoules.
Is it possible to go lower?
Yes, you could put a resistor in parallel to this, and that would drop down. But it would also reduce the efficiency of it. So there would be a trade.
I think we should open it now and